All right, today we're going to look at more of what we did in class with finding the moment of inertia. Some of you said you wanted to see it, and we're going to do this by integration, which is not easy. So, this may take a while, this may be confusing. I'm not going to test you on this. It's a little bit of a preview of things that we might see as we move forward and look at as we move forward and look in our electricity unit. But right now I'm not going to test you over this information. So if it's going to confuse you, if it's going to make you freak out about all of the things that you need to know, then stop. Don't even worry about it. If you want to see some cool math stuff happen, which is a weird way to spend your weekend time, then let's continue. So the first thing we're going to look at is a rod, and we're going to find the moment of inertia of that rod by integrating. So here's our rod. It has a length of L, total mass M, and we're going to look at the rod about its center. That's important. So first thing we're going to do is find the mass from the center point. Basically, we need a place to call 0. And for a moment of inertia, that becomes our pivot. So, as we do this, we need to define our piece of dm. dm is going to be that tiny slice right there. Now, mass in general is rho, my density, times the volume. But we're looking at a tiny slice of mass, so the differential piece of mass is going to be rho times my differential piece of volume. We need to define what that differential piece of volume is. Now, volume in general is length times width times height. So I want to look at what the length of my dV is, my width, and what my height are. So length is going to be along that L dimension. We're going to call it dx. Width and height we don't know about. So we're just going to make them up. And since we already have W and H written down, width is going to be W and height is going to be H. So my differential piece of volume is WH times dx. So we're going to take that and plug it in for dV. Now we're going to integrate both sides. And again, we're just finding the mass first because we're going to use the mass after we look at the moment of inertia. So we're going to integrate both sides. Now, when we integrate on the dx side, I have limits. I'm starting at that blue line. So if I swing all the way over to the left end, my lower limit, the place where I start, is going to be negative L over 2. The top, if we swing all the way over to the right, is just L over 2. So everything, okay, so the dm side just turns into m. When I add up all my tiny pieces of m, I get my total mass. And then I'm going to pull out everything that doesn't change when I go to a different slice. So the rho doesn't change, the density is the same, the width is the same, and the height are the same. So the only thing we're integrating is our differential piece of length. And our limits are still negative L over 2 to L over 2. Now, when we differentiate our little piece of length, and I'm just going to go ahead and write this out as I talk, but we're adding up all little tiny dx's, that's just going to give me the total length of my rod. Just like adding up all the tiny masses gave me the total mass of my rod. So I'm going through all the steps quickly of showing you how we do that. But again, when it's done, it just comes down to rho times width times height times length. Rho times the volume, which shouldn't be too familiar to you. Now, we plugged in the limits, but like I said, we just added up all the little pieces of dx to get our total length. So in this case, and this case only, this is going to be true regardless of where my starting point is or regardless of where my pivot is. The rod's that only place that's going to happen because nothing is crazy, nothing's changing all at once. So it's true for all points, not just at the center. Now things are about to get fun. We're going to look at finding the moment of inertia. So let's start with what our basic formula for moment of inertia is. I equals, so we're going to look at the moment of inertia about the center. We choose a center point for that. So I is going to be equal to r of the integral of r squared dm. Since we've already defined our dm over here, it's rho dv, which is rho times w times h times dx. We're just going to substitute that in directly for dm. So I'm going to put it in there. Rho times width times height times dx. And just to make things clear, we don't really have r's here. And since dx was part of this, my radius is just changing along that r line, that x line. So everywhere I see an r, I'm just going to put an x. And my limits are, again, negative L over 2 to L over 2. So, for this integral, we're going to pull out everything that's not changing with every piece of dm that I go to. So that means x squared stays inside, dx stays inside, but everything else comes out. So we have rho wh on the integral from negative L over 2 to L over 2 of x squared dx. Now, x squared dx is easy. We raise it a power, divide by the new power. So everything else stays the same, but now it's x cubed over 3. And as always, we have to apply our limits. So we plug in our initial value, and we plug in our final value. And so since it's, I'm going to go ahead and move the 3 out of there, just because it's going to make it a little bit easier. So rho WH divided by 3. So it's going to be L over 2 cubed minus negative L over 2 cubed. Now since it's cubed, those negative signs stay in there. And it's going to go from L over 2 cubed to L cubed over 8. Negative signs cross out. So L cubed over 8 plus L cubed over 8 is L cubed over 4. So what we're going to get, 3 times 4 is 12. So let's let this go out. My moment of inertia is that term times L cubed over 12. And we just said that was mass. So, moment of inertia about the center is mass times L squared over 12, which is exactly what we had in our chart. This is where it comes from. It's a bit of a complicated integral. Now, just to have some fun, what we're going to do is look at the moment of inertia about one end. So all we're doing here is changing our limits. Everything else looks the same, so we're going to start there. But our limits are, instead of going from negative L over 2 to L over 2, are going to go from 0 to L. That's what it means to start at one end. And the mass part's still the same, we're just changing our limits. So my moment of inertia is going to be rho times W times H times L cubed over 3. So we'll let that play out. So it's x cubed over 3 from 0 to L. We're going to plug in those limits. No big deal. So it's L cubed minus 0 cubed. And we're going to do just like what we did before, split it up into what I know is my mass, rho times W times H times L, that's my mass, times what I have left over, which is L squared over 3. So since that's the mass, we go ahead and plug in the mass, and I get 1/3 ml squared. I realized that this was fast. So if you need to take notes over this, go ahead and pause and write it down. That's okay. So that was a lot. So we are going to now move on to a solid disk. Okay? We kind of looked at this already, but we're going to look at our disk. So it's solid, it's colored in, has a radius of capital R. And again, like always, we're going to start with mass equals rho times volume. So my differential piece of mass is rho times my differential piece of volume. And just like before, for that differential piece of volume, we're going to look at length and width and height. So that's my dm, is that circle in the middle. The length of that circle, the length of that red line, is just the circumference of the circle. So the length of that red line, that's my dm. So the length of that red line is 2 pi r. The width is just the tiny width there. That's my differentiable piece. It's a tiny, tiny, tiny ring inside of that solid disk. So the width of that tiny ring is going to be my dr. And then the height, because it's a solid disk, is whatever the cylindrical height is. I don't know how else to call it but h. So my dv is 2 pi r times h times dr. So we're going to take that, plug it in for dv. And now we're going to integrate both sides. Integrate dm and integrate the other side from 0 to capital R. And the reason we're doing that is because we're starting at the very center of the circle and we're ending at the very edge of the circle. And what we did in class today, we had different limits because we didn't start at the very center. So we add up all our little pieces of dm and that gives me m. Then we add up, well, then when we do the other side, everything comes out of that integral except for the r dr, because everything else is constant. So we go ahead and write m equals all the constant stuff times the integral of r dr from 0 to r. That's a very easy integral to take. The integral of r with respect to r is r squared over 2. So all that stuff stays the same. And this is just r squared over 2 from 0 to r. It's very easy to plug in the limits here. So we do final minus initial. Going to go ahead and, yeah, r squared over 2 minus 0 squared over 2. My halves cross out, which is good news. And so for my mass, I get rho times pi times h times r squared. Which interestingly enough, this pi times h times r squared thing is just the volume of a cylinder. So it's rho times the volume of my cylinder. Probably didn't even have to go through all of that, but I kind of want you used to seeing this integral. So now that we have the mass, we're going to start looking at the moment of inertia. So we're always going to start with the integral of r squared dm. We already know what our dm is. It's the rho times 2 pi r h dr. We're going to multiply that by an extra r squared. Going from 0 to r again, and what we're going to do is pull out everything that's constant and just leave all of the r's and the dr inside of that. That's the only thing that changes as we go to different pieces of dm. So everything comes out, rho times 2 pi times h on the integral of r cubed dr from 0 to r. So the integral of r cubed is just r to the 4th over 4. And we're going to apply our limits to that. R to the fourth over 4 from 0 to R. When we do that, that's a lot of big R's, but it's 1/2. Go ahead and apply that fourth times rho times pi times h times R to the fourth. I know it says minus 0. Now, what I'm going to do is break up that R to the fourth to R squared times R squared. And I'm doing that so that you can see the mass in the middle right there. Mass, mass. So I'm just going to directly substitute for the mass for that. And I get 1/2 mr squared. Sorry, that doesn't look very much like a 2. So, that's for a disk. And now, if you're feeling confused, please just don't watch the sphere. It's going to be hard. It was tough for me to figure out, so there we go. Now, if I have a hollow ring before we go into a sphere, just remember that from what we did in class, if I change the limits, I can do it for a hollow ring. But that's going to affect both the mass, because making it hollow takes away some mass, and the moment of inertia. It's good to keep in mind. So, let's get crazy. Let's do the sphere. The sphere is hard because I'm not allowed to do spherical shells with this. There's an extra term that needs repeating. So, we're going to take a sphere, and instead of building up spherical shells like we're used to, we're going to take that sphere and cut it up into vertical strips, if that makes sense. So, here's a vertical strip. Drawing this was kind of a bear, so bear with me here. So it's not straight vertical. I want to give you sort of a view of it, but we're going to take these slices, these vertical slices, okay, and we're going to say that the radius of each of these vertical slices is lowercase r. I got a little creative. The radius of my big sphere is capital R. You'll see how all of it plays together. Speed that up a little bit. So, I wanted to make it look like a sphere. And then we'll start defining our terms a little bit. So, that's my axis. Alright, and we still want it to kind of look good. So we'll go back and color that in some. I got very concerned with things looking good for some reason. Alright, might look more like a dotted line, which is nice. So that's going to be my x-axis for all intents and purposes. Now, as we build this up, we're going to say the distance from my center point to my disk is going to be x. My center point is obviously 0. We're going to say, as always, the radius of the thing, the big sphere, is r. And then that length that I'm drawing right there, the radius of the disk, is little r. And so when we integrate, we're going to go from back there, negative r, to up there, positive r. And again, that is my x-axis. Okay, so The width of my slices we're going to call dx. Each slice is a disk. And we already have an expression for the mass of the disk. We had it back there. It was rho times pi times r squared. Now in this case, r squared is staying the same, and the thing that changes my little dx is that h. That's the height of my tiny cylinders, if we remember that. So if I want to make this differentiable, dm is rho times pi times r squared dx. It's kind of important that we set it up that way. Now, here's the problem. X and r are two different things. So we're going to need to, again, yes, take the integral. But I've got r's and I've got dx's. That represents a problem. So I'm going to redraw the triangle that you see up there in this sphere. Okay? The base of that triangle is x, the height of that triangle is r, and the hypotenuse is capital R. So, what I want to do is use this triangle to substitute an expression for r squared. And this is why this is confusing, and this is very difficult. Okay? So, r squared is going to be capital R squared minus x squared. Now, that's a nice expression that we can use because capital R, the radius of the sphere, is going to stay the same regardless of, sorry about the dog, regardless of which vertical slice I'm looking at. And x is what I'm integrating with respect to, so we expect that to change. So this expression has something I need and something that's constant, which is wonderful. So we're going to plug that in. And you may not have gotten this far yet. Okay, and then we're going to go from negative r to r. You may not have gotten this far yet in calculus, but you've done it with derivatives. If you have, a polynomial function, then you just take the derivative of each term. Well, that works here too. If you have addition and subtraction inside of an integral, you're just going to take the integral of each term. So that's what we're going to do. I think I just wrote it twice. Super helpful. So, it's the integral of r with respect to x, and that's just constant, r squared with respect to x, minus the integral of x squared with respect to x. So as we take this integral, the r squared comes out, and just have rho pi times r squared times x from negative r to r. So it's just the integral of dx. We'll go ahead and pull that out. And then this is going to be x cubed over 3 from the same limits. We're going to plug in our limits. And the nice thing about this is it's just going to be, for the first one, instead of x, it's going to be r minus negative r. So just 2r. For the second one, it's going to be 2r cubed over 3. And you can work that out on your own by plugging those limits in. We'll do final minus initial. Yeah, oh, I just did it. R minus r. And then r cubed over 3 minus r cubed over 3. We'll make it easy for you there. So, skipped ahead a little bit. Sorry about that. We're going to clean that up. So, rho pi times 2r cubed minus 2r cubed over 3. And that gives me rho times pi times 4/3 r cubed. Alright, well that was Tough. We get to do it again, it's going to get tougher. But if you'll notice, it's just rho times the volume of a sphere. Now we're going to look at the moment of inertia. So how we have to remember that for a disk, the moment of inertia was 1/2 mr squared. Now the disks that I made are my little pieces of dm. So each disk represents a differential piece of the moment of inertia. So I have di, a differential piece of my moment of inertia, is equal to 1/2 r squared dm. This can be a confusing step. We do it in physics for calculus all the time. But we take something that was a whole value, a disk, and the moment of inertia for a disk, and we start adding these tiny infinite disks together. So each single disk is a differential piece of mass, and it's a differential piece of the total moment of inertia. And honestly, if this gets to be too much for you, just look at that wonderful drawing of the sphere and the disk. Be amazed at how awesome it is. I'm kidding, that's terrible. So, we're going to take the integral, and we're going to go again from -r to r, because that's the little values of the disk that I'm adding together. Now, all my little pieces of di just turn into I. And what we're going to do is substitute what we had for dm before in for dm. Again, nothing surprising for what we've done so far. Now, here's where it gets crazy. I have a dx and an r squared, and another r squared. So I have r cubed. Go ahead and write that in. Sorry, r to the fourth, not r cubed. I apologize. From -r to r. Now, this is a problem, having r to the fourth and dx in there together. So we're going to use the same expression that we used before, but that was for r squared. So what we're going to look at apologize for that. What we're going to look at is r to the fourth is equal to r squared squared. So we're going to plug in what we had for r squared and then square that expression. So 1/2 rho pi times the integral of capital R squared minus x squared quantity squared dx. Okay, that looks terrible. What we can do, I left off a squared, apologize profusely for that. We can FOIL that out until we get a nice normal polynomial expression that we know how to deal with. Okay, so instead of r squared minus x squared quantity squared, it's going to be r to the fourth minus 2r squared x squared plus x to the fourth. Then we're going to apply the integral to each little piece of that. So let's FOIL it out. R to the fourth minus the middle term, 2r squared x squared plus x to the fourth. All in terms of dx. I realize that Miss Cox, in all likelihood, would have you do it some other way. I'm just not that good at calculus. So, we're going to take this integral and we're going to apply it to each individual term, and we're going to pull out everything that's not an x. So the first term, r to the fourth, doesn't have any x's in it. That can stay outside of my integral. The second term, 2r squared comes out, and now it's just the integral of x squared with respect to x from my limits. And the third integral is just the integral of x to the fourth with respect to x. Go ahead and close that off. Didn't close it off. So, the first integral is just going to give me x from r to negative r. The second integral is going to give me x cubed over 3 from r to negative r. And the third integral is going to give me x to the fifth over 5 from r to negative r. As we plug in our limits, it's 2r for each one of those. And we'll go step by step just so that you can see it. So, the first one gives me x, the second one gives me x cubed over 3 from the same limits, and it's trying to cram everything in on one page. And the third one gives me x to the fifth over 5 for the same limits. And we plug the limits in for each one, cancel out the negative signs. Again, I'm going fast. Don't worry about how fast I'm going. You can always pause it. So that is going to be 2r, and then it's 2r squared times 2r cubed over 3 plus 2r to the fifth over 5. So at this point we are done with all of the calculus. So now we're going to combine like terms and come up with a common denominator. We know that common denominator is going to be 15. So 1/2 rho pi times 2r to the fifth over 15. Oh, okay. So no, we won't do that 15 yet. Just 2r to the fifth minus 4/3 r to the fifth over 3 plus 2r to the fifth over 5. Now our common denominator is 15. So it's going to give me 30r to the fifth over 15 minus 20r to the fifth over 15 plus 6r to the fifth over 15. Whew. So 30 minus 20 plus 6 is 16. So I got 1/2 rho pi, my goodness, times 16 over 15 r to the fifth. Sorry, that's a 15. So the half goes away, and that gives me just 8 over 15 rho pi r to the fifth. And we're going to break it up conveniently, okay? So I know that I've got 4/3 for my mass. So we'll put everything together that's mass. 4/3 rho pi r cubed. And what I'm left with after I do that is 2/5. Hopefully you can figure that out looking at it. 4/3 times 2/5 is 8/15. And I have r squared left over. We plug in for the mass. That's mass. Plug it in, and I got 2/5 mr squared. And that is that. If you ever wanted to know how to do that, now you know how to do that. Again, I'm not testing you over this. I'm showing you in case it might ever come up in casual party-like conversation. I doubt it will. If it does, it's a terrible party. You should probably go home. So, thank you for listening if you made it this far, and I'm sorry that it was 35 minutes long.